Welcome to Tomorrow Unveiled. It is Wednesday, January 28, 2026. I'm your host, and today we have a monster of a show. We are looking at a stack of reports, industry filings, and scientific papers from just the last 7 days that, quite frankly, make the last decade of energy news look like a warm-up act. As always, I'm joined by my co-host and resident expert to try and make sense of it all.
It's good to be here. And you aren't exaggerating. I mean, I've been covering this sector for a long, long time. Usually we're talking about incremental gains,
Yep.
a 0.5% efficiency bump in a solar cell or a new tax credit.
Yeah.
But the file from our research team this week, it reads like a completely different industrial era.
It really does. The team has titled this Tomorrow Unveiled Deep Dive, Green Code Hot Core. Now, I have to be honest with you, right off the bat, that sounds a bit like marketing buzzwords. It sounds like the title of a bad sci-fi paperback. Are we just hyping up a good week, or is there actually a structural shift here?
I get the skepticism. I really do. We hear revolution every other week.
Right.
But green code, hot core, it isn't a slogan. It's a description of a mechanical convergence we saw solidify just between January 21st and, well, today.
Okay, so convince me. Unpack that. What does that actually mean?
Think of it as two massive gears locking together for the first time. The green code part is, well, it's two things at once. First, it's the aggressive integration of AI into the physical sciences. We're talking about using compute to just brute force discovery in physics and chemistry.
Right, finding new materials, new reactions.
Exactly. But green code is also the demand side. It's the sheer, almost terrifying amount of electricity these new AI data centers are starting to consume.
So the code is the brain, but it's a very, very hungry brain.
It's a ravenous brain. And that hunger is forcing the entire grid to pivot. For 20 years, the energy transition was all about harvesting the weather, solar panels, wind turbines. It's variable, it's low-density power. But the data this week, it confirms a hard pivot toward the hot core.
Hot core.
We are seeing capital and technology just flood into high-density, firm, thermal energy. Sources that rely on heat and physics, not the weather. So we're talking fusion, advanced fission, and deep geothermal.
Okay, so let me see if I have this right. The argument is that the code needs the core to run because wind and solar just can't keep up 24/7. But at the same time, the core needs the code to even exist because the physics are too hard for humans to solve alone.
That is the thesis. It's a symbiotic loop, a feedback loop. And the evidence from just the last 7 days, it just lines up perfectly. We have the U.S. government launching something called the Genesis mission, which is effectively creating a computational NATO for science.
But computational NATO, I like that.
Then you have Meta Facebook buying enough nuclear power to run a small country, and maybe most significantly, a physics breakthrough in China regarding the Greenwald limit. It suggests we might be very, very wrong about how far away fusion really is.
The Greenwald limit. Okay, we are definitely going to spend some time on that because the notes on that look incredibly dense. But let's start with the green code. I want to look at this Genesis mission announcement from yesterday, January 27th. This involves the U.S. Department of Energy, Japan's Riken Institute, and then NVIDIA and Fujitsu.
Right. This is what's called a public-private quadrilateral agreement.
It sounds fancy, but isn't this just another memorandum of understanding? Governments sign these things all the time. They take a photo, and then nothing happens for 5 years. Why is this one in our research stack?
It's a fair question. The reason is because of the specific technical architecture they agreed to. Usually these agreements are about sharing funding or, high-level goals. This one is about sharing a software stack, an open source stack to democratize AI for science. They are trying to solve what's known as the inverse design problem.
Inverse design. Okay, break that down for me.
Okay, traditionally, material science is just trial and error. Let's say you need a new crystal for a battery cathode that can handle higher voltage. The old way, the Edison way, is to mix some lithium, some nickel, maybe some manganese. You bake it and you test it. If it fails, you change the ratio and you try again and again and again. It's painfully slow. It's incredibly expensive.
It's the baking a cake analogy, right? You bake 1,000 different cakes to find the one that tastes good.
It is. But let's get a bit more technical because the cake analogy kind of hides the insane complexity here. We aren't just mixing flour and sugar. We are dealing with quantum mechanics. To really predict how a new material will behave, you have to solve the Schrödinger equation for every single electron in that crystal lattice. That is computationally brutal. It's a method called density functional theory, or DFT.
I remember DFT from college physics. It takes a supercomputer days, maybe weeks, to simulate just a handful of atoms, right?
Exactly. So you can't just simulate everything because it would take centuries. The search space is too big. But this new partnership, this Genesis mission, is deploying what they call generative molecular models. They are training AI on all the known physics and chemistry data we have, so that the AI can approximate those DFT calculations in seconds, not days.
So wait, instead of the supercomputer grinding through the hard math for a week on one combination, the AI just looks at the pattern and says, based on everything I know about electron density and quantum states, this structure will probably work, and it does it instantly.
That's the green code. That's the breakthrough. And it allows for inverse design. Instead of mixing ingredients to see what you get, you tell the AI the properties you want. You say, I want a material that conducts at this voltage, withstands this temperature, and oh, by the way, doesn't use any cobalt. The AI runs the generative model backward and gives you the chemical formula.
But, and I have to play devil's advocate here, we know AI hallucinates. We see it all the time with chatbots making up legal cases or historical facts. If an AI hallucinates a chemical formula and you go and build it, couldn't that be incredibly dangerous? Or at the very least, a massive waste of time and money?
That is the single biggest risk.
Yeah.
Absolutely. And that's why this partnership is so critical. They are building what they call a verification loop. The AI proposes a new material and then, and this is the key part, automated robotic labs at Argonne and Riken physically synthesize a tiny sample of it.
Oh, wow.
They test it right there, and they feed that real-world data back into the AI model. It grounds the AI in physical reality, keeps it from, drifting off.
Okay, so it's not just software. It's software connected to a robotic hand that's actually mixing the chemicals. That makes a lot more sense. But let's look at where this is being applied right now. We saw a fascinating note about digital twins in the fusion sector. Commonwealth Fusion Systems, or CFS, is working with NVIDIA and Siemens.
Right, this is where the green code moves from discovering new materials to controlling pure chaos. So CFS is building this SPAC reactor up in Massachusetts. It's a tokamak, basically a magnetic bottle designed to hold a tiny star.
But they aren't just building the physical machine.
No, that's the thing. They are simultaneously building a digital twin of it, a perfect virtual replica. But again, let's go deeper than the buzzword, because it's important. A tokamak plasma is one of the most unstable things humans have ever tried to create. It's subject to these things called neoclassical tearing modes, or NTMs.
It's NTMs. It sounds like a 90s boy band.
It does, but it's much more destructive. It's a magnetic island that spontaneously forms inside the plasma. If that island grows too big, it tears the magnetic field apart. The plasma, which is at 100 million degrees, touches the wall of the machine, and the whole reaction just crashes. This is called a disruption.
And a disruption in a commercial reactor isn't just an oops, it's a billion-dollar problem.
It can literally break the machine. It can melt components. So you absolutely have to predict these NTMs before they happen. Which brings us to a study the research team highlighted from the Hefei Institutes in China this week. They've been working on the control system for their East reactor, and they built an AI they call the locked mode predictor.
The notes here say it achieved 94% accuracy. That's incredible. But the number that really stood out to me was the warning time. 137 milliseconds.
Right.
To me, 137 milliseconds it's a blink. It's literally faster than a human can react. Is that actually useful? Can you really stop a star from exploding in a tenth of a second?
It's a great question, and the answer is yes. In the world of magnetic confinement fusion, 137 milliseconds is an eternity. It's an absolute luxury. Think about the physics. These magnetic instabilities, they grow at what's called the Alfvén timescale. We're talking microseconds, millionths of a second. Getting a 137 millisecond warning is like getting a weather forecast a month in advance. It allows the control system to steer mirrors, inject carefully aimed microwave pulses. It's a technology called electron cyclotron resonance heating. And you can target that specific magnetic island to smooth it out before it grows.
So it's like an AI sniper taking a shot at a tiny tumor inside the plasma before it can become cancerous.
That is a perfect analogy. Without the AI, the green code, predicting that instability, that the control system is just reacting blindly after the fact. It's too late. With the AI, it's proactive. And this effectively proves that you can reliably stabilize high-performance plasma. That's a huge step.
Okay, so the AI is the pilot that's keeping the plane in the air. But let's flip the coin here. The pilot is hungry. The pilot is starving. We cannot ignore the story out of Menlo Park this week. Meta, the parent company of Facebook and Instagram, announced a procurement strategy for 6.6 gigawatts of nuclear power.
This is the hot core demand shock we were talking about. This is the other side of the equation.
6.6 gigawatts. Let's try to contextualize that for a minute. That is not a data center. That is a fleet of data centers. That's a national-level power commitment.
It's the equivalent of 6 or 7 standard, large-scale nuclear reactors. It is roughly the power consumption of the entire state of Massachusetts on a mild day for one company.
So why nuclear? Why not just blanket Nevada in solar panels? It's cheaper per kilowatt hour, isn't it?
On paper, yes, solar is cheaper per unit of energy generated, but solar has a capacity factor of maybe 25–30% in a good location. It works when the sun is up. AI data centers, especially for training these massive models, have a load profile that is completely flat. They run at 100% capacity, 24 hours a day, 7 days a week, 365 days a year.
They don't sleep.
They don't sleep. They don't take holidays.
Oh.
And our research team pointed out that an AI query, like asking a chatbot a question, consumes roughly 10 times the electricity of a simple Google search. So if you run a data center on solar, you need massive, massive batteries to cover the night. That's expensive. But you also need to cover the Dunkelflow, the dark, windless weeks in winter. The cost of batteries to cover a week of downtime for a gigawatt-scale data center is astronomical. It's not feasible. Meta has clearly done the math. They realized that to have firm, reliable power that never, ever blinks, they need thermal generation. They need the hot core.
It really feels like big tech is becoming the new utility sector. They aren't just customers anymore. They're becoming the developers.
They have to be. The grid isn't moving fast enough for them. If Meta waits for the standard utility procurement process, they'll get that power in 2040, maybe. Their AI roadmap needs it in 2030.
Which brings us directly to the hot core itself. If Meta wants nuclear, they're probably looking at advanced fission, SMRs. We'll get to that. But the news this week suggests fusion might not be the 30 years away joke we always make. We need to talk about the Greenwald limit.
Yes, this is the heavy physics news of the week. This is a big one.
The research team flagged a breakthrough at the East Reactor in China, the artificial sun. They claim to have broken the Greenwald limit. Now, I've heard of the speed of light limit, but what on earth is the Greenwald limit?
So Martin Greenwald, a physicist at MIT, defined this back in 1988. It's what's called an empirical limit. It's not a hard law of physics, it's an observation from experiments. Basically, we observed over and over that if you increase the density of the plasma in a tokamak past a certain point, the plasma becomes turbulent and crashes. It puts a ceiling on how much fuel you can pack into the engine.
So it's a density ceiling. Okay, but why does that matter so much? If I can't make the plasma denser, can't I just make the reactor bigger to get more power?
You can. And that's exactly why the ITER project in France is so gigantic and so expensive. But here is the critical equation, the one that governs everything in fusion economics. Fusion power output scales with the square of the pressure. And pressure is largely determined by density and temperature. So think of it as power being proportional to density squared. The formula is tempano propto N22.
Okay, let's pause on the math because this is important. Power is proportional to density squared.
Right. So if you can find a way to double the density of the plasma, you get 4 times the power output. If you can triple the density, you get 9 times the power.
So density is the leverage point. It's the magic multiplier for the whole system.
It's everything. If you are stuck below the Greenwald limit, you are leaving massive, massive amounts of power on the table. You're forced to build a giant cathedral of a machine just to get a gigawatt out. But if you could break that limit, if you can operate at a higher density, you can potentially build a much smaller, much cheaper machine and get the same amount of power.
And the team at the East Reactor in China broke it. How? Did they just turn the knob to 11 and hope for the best?
Not quite. It's much more subtle than that. What usually happens when you push the density too high is that the edge of the plasma cools down, becomes unstable, and then the whole thing collapses inward. The Chinese team found what they're calling a density-free regime. They did it by using a specific type of fueling pellet injection and very carefully managing the magnetic shear right at the edge of the plasma.
Pellet injection? You mean like shooting frozen BBs into a miniature sun?
That's literally what it is. Tiny frozen pellets of deuterium and tritium fuel fired at incredibly high speed deep into the core of the plasma. What this does is it fuels the center of the reaction without cooling down and disrupting the delicate edge. By doing this, they maintained a stable plasma at densities well above the long-standing Greenwald limit.
This sounds like it completely changes the economics of fusion. If I can get 4, maybe 5 times the power out of the same size machine, the cost per kilowatt hour must just drop like a rock.
It potentially transforms fusion from a multi-decade science experiment into a competitive industrial power source. It validates that the tokamak design, which is the most common one, isn't a dead end. It has a path to commercial viability.
Speaking of designs, we have to talk about General Fusion. They were in the news on January 22nd. They're going public via a SPAC merger.
Right, at a valuation of nearly $1 billion.
Now, General Fusion doesn't use a tokamak. They have this, I call it the steampunk machine. Can you describe what they are building? Because it sounds absolutely wild.
It is wild. It's a completely different approach called magnetized target fusion. Imagine a large sphere filled with molten lead lithium. They spin the sphere very fast, and the centrifugal force creates a vortex, a hollow cavity right in the center.
Okay, so you have a spinning wall of liquid metal.
Exactly. Then they inject a plasma target, a self-contained little smoke ring of plasma, into that hollow center. And then, this is the steampunk part, there are hundreds of pneumatic pistons on the outside of the sphere, and they all fire at the exact same millisecond. They slam the liquid metal wall inward.
Like a collapsing lung, but made of metal.
It's a perfect description. It crushes the plasma. This rapid compression heats the plasma to fusion temperatures for just a fraction of a second, and you get a pulse of energy.
But why do it this way? It sounds so mechanical. Why not just use magnets like everyone else?
Because it elegantly solves one of the biggest problems in fusion, the neutrons. A fusion reaction releases a flood of high-energy neutrons. In a standard tokamak, those neutrons slam into the solid steel walls of the reactor, making them brittle and radioactive over time. Material degradation is a huge issue. In General Fusion's design, the liquid metal is the wall. The neutrons hit the liquid, which absorbs their energy as heat and also breeds more tritium fuel for the next shot. But the liquid can't break or become brittle. It's already liquid. You just pump the hot liquid out, run it through a heat exchanger to make steam, and then pump it back in.
So it solves the material science problem by removing the solid material from the equation.
Correct. And the fact that they're going public via a SPAC now means they believe they're getting very close to demonstrating Lawson criterion net energy gain on their new machine, the LM26.
It's just fascinating to see the divergence in approaches.
Yeah.
You have the high-tech magnetic confinement controlled by AI on one side and this brute force mechanical piston approach on the other.
That's what a healthy, maturing, deep tech ecosystem looks like. Multiple shots on goal. You don't know which one will win, so you back several.
There's one more fusion story, and this one, to me, felt almost poetic. The Bull Run Fusion Campus in Tennessee.
This is symbolic perfection. Bull Run was a coal-fired power plant for decades. It burned rocks, dug out of the ground to boil water. It shut down a few years ago. Now, a company called Type 1 Energy, along with Oak Ridge National Lab and the University of Tennessee, is taking over the site.
And they are building a stellarator testing facility there.
Right. A stellarator is the other magnetic design, the twisted donut. It's incredibly complex to build, but theoretically more stable than a tokamak. But think about the asset they are reusing. That site already has a massive grid connection. It has access to water for cooling, it has roads, infrastructure, and it has a local workforce that knows how to operate and maintain a power plant.
This addresses the whole NMB issue, right? Not in my backyard. People in that community are already used to a power plant being there. They probably welcome the new jobs.
And they want the high-paying jobs back. We are seeing this trend of coal to nuclear, or now coal to fusion, popping up everywhere. You keep the most valuable and hard-to-build part, the transmission lines, and you just swap out the heat source. You replace the coal furnace with a hot core.
It's recycling on a gigawatt scale. But let's be realistic. Fusion is still, let's be generous and say the late 2030s for commercial power on the grid. Meta needs power now. That brings us to fission. The SMR's small modular reactors.
Right, the now technology of the hot core.
We've been hearing about SMRs for at least a decade. NuScale had a big project in Utah that got canceled just last year because the costs spiraled out of control. Why should we believe the news this week is any different?
That is a very fair question. The NuScale cancellation was a major blow to confidence in the sector. But the news this week from the Tennessee Valley Authority, or TVA, is different because of the scale and the commitment. TVA launched a program to deploy up to 6 gigawatts of SMRs.
There's that number again. 6 gigawatts.
It seems to be the magic number for an industrial-scale commitment. I think the difference now, after the NuScale failure, is the realization that SMRs only work economically if you commit to a whole fleet. If you try to build just one first-of-a-kind SMR, it's going to be incredibly expensive. All the design and regulatory costs are loaded onto one project. But if you commit to building 20 of the exact same design, you get the learning curve cost reduction.
It's the Henry Ford model. The first Model T was a handcrafted, expensive prototype. The millionth one was cheap because it came off an assembly line.
That is the exact analogy. SMRs are designed to be factory built. Traditional nuclear plants are like the pyramids. They are massive, custom civil engineering projects built on-site over a decade. SMRs are supposed to be like Boeing 737s. You build the reactor module in a controlled factory environment, you put it on a train or a barge, and you ship it to the site.
So your quality control goes way up and your construction and weather delays go way down?
That's the theory. And what's different now is that we're seeing actual concrete being poured. A company called Kairos Power is building their Hermes test reactor in Oak Ridge, Tennessee. The foundation work is visibly underway. You can see photos of it. This isn't just a PowerPoint slide anymore.
Okay, but there is a bottleneck, right? An elephant in the room. We can build the engines, but do we have the gasoline for them? I saw a lot of chatter in the research notes about HALEU.
HALEU, high-assay, low-enriched uranium.
Explain this. Why can't we just use the same uranium fuel we use in our existing nuclear plants?
Our existing fleet of large plants, they use uranium that's enriched to about 3 to 5% of the U-235 isotope. That works fine for big, traditional light water reactors. But if you want a small, compact, hyper-efficient SMR that can run for years or even decades without refueling, you need much denser energy. You need fuel that is enriched up to 19.75% U-235.
19.75%. That's a very specific number. Why stop there?
Because at 20% enrichment, uranium is officially classified as highly enriched uranium, which is weapons-grade material. So 19.75% is the legal and non-proliferation limit for commercial fuel. The problem is, for decades, the only major commercial supplier of HALEU on the global market was Russia.
Well, that's a strategic nightmare given the current geopolitical climate.
It is a massive, massive vulnerability. The U.S. and Europe effectively had zero domestic capacity to produce this fuel. But this week, the Department of Energy finalized the first major contracts to jumpstart a domestic U.S. production chain. And on the private side, we saw a startup, Standard Nuclear, raise $140 million in a Series R round, specifically to build HALEU enrichment and fuel fabrication capacity. And Kairos Power, the company building the Hermes reactor, finalized their own contract to receive the first batches of HALEU for their fuel pebbles.
So the supply chain is finally waking up to meet the demand from the reactor developers.
It's a race. The reactor developers are moving, and the fuel supply chain is sprinting to catch up. If they don't meet in the middle at the right time, we'll have brand new finished reactors just sitting there empty. But the investment we saw this week suggests that the market now believes they will make it.
It's incredible to watch an entire heavy industry, from mining and enrichment to fabrication, essentially reboot itself in real time.
It's nothing less than the reindustrialization of the Western nuclear sector.
We are going to take a very quick break. When we come back, we are going to look at the third leg of the hot core stool. Everyone talks about nuclear, but there is a company that just filed for a massive IPO that drills for heat, not oil. And we'll look at the grid reality check, why the wind turbine stalled out this week and what a Dunkel float actually feels like to a grid operator. Stay with us on Tomorrow Unveiled. Before we jump back into the heat, I just want to talk to you directly for a moment. We pour through thousands of pages of reports and data to bring Tomorrow Unveiled to you, and if you're finding value in it, there are a couple of really simple ways you can help us out. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners. It takes 10 seconds, but it makes a massive difference in our visibility.
And we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the shift to green code and a hot core. Now, back to our deep dive. We've done fusion. We've done fission. Let's talk geothermal.
The sleeping giant of the hot core.
You know, usually when I think about geothermal energy, I think of Iceland, or maybe a hot spring in Japan, or Yellowstone. You need a volcano in your backyard, right?
That was old geothermal, what we call hydrothermal systems. You needed three things to be in the exact same place, naturally. Intense heat close to the surface, water, and permeability. Natural cracks in the rock for the water to flow through. That combination is really rare, and that's why geothermal has always been a niche player and never really scaled.
But the research this week highlights a company called Fervo Energy. They just filed confidentially for an IPO, and the valuation numbers floating around are exceeding $2.8 billion. That is a lot of money for a niche technology.
That's because Fervo isn't doing old geothermal. They are the leader in EGS-enhanced geothermal systems. And to be blunt, it's fracking for heat.
Fracking, okay. That word carries a lot of political and environmental baggage.
It absolutely does. But we have to look at the technology transfer here. The shale gas revolution in oil and gas perfected two key technologies: horizontal drilling and precision hydraulic fracturing. Fervo is taking that exact tech stack and applying it to hot, dry rock. They drill down a couple of miles, turn the drill bit 90 degrees, drill horizontally for another mile, and then they pump water down at high pressure to fracture the rock and create an artificial network of cracks. They create their own reservoir.
So they don't need to find a natural hot spring. They essentially build their own radiator deep underground.
That's a perfect way to put it. They create a closed loop. They pump cold water down one well. It flows through the man-made fractures, absorbing heat from the rock, and comes up another well as superheated steam to drive a turbine. And because hot rock is literally everywhere if you just go deep enough, this makes geothermal deployable almost anywhere in the world, not just near volcanoes.
But what about the risks? I remember reading about projects in Switzerland getting shut down because they cause small earthquakes. If you are deliberately fracturing rock deep underground, aren't you inducing seismicity?
That is the primary public concern and the primary technical risk. However, the industry has learned a lot since those early projects. They've now widely adopted what they call traffic light protocols. They surround the drill site with incredibly sensitive seismic monitors. If they detect even a microtremor, a tiny vibration that no human would ever feel, that's a yellow light. And they dial back the pumping pressure immediately. If it continues, it's a red light, and they stop completely. Fervo claims their data shows they can manage this safely by staying far below the pressures that would cause any felt seismicity. And, well, a $2.8 billion valuation suggests the market is starting to agree.
The drilling speed statistics in the research report were pretty impressive.
They're showing incredible learning curves, just like we saw in the shale industry. The report noted that in 2020, it took Fervo 310 hours to drill one of their wells. In 2023, they did it in just 110 hours. They cut the time and the cost by 2/3 in just 3 years. That is the green code of data analytics and operational optimization at work.
And they have a massive project, Cape Station in Utah, coming online this year.
Yes, a 400-plus megawatt project. And guess who the primary customer is?
Let me guess. One of the big tech companies.
Google. Google signed a massive PPA, a power purchase agreement, for the output. Again, it's the same story. AI needs 2047 firm, carbon-free power. Geothermal is one of the only renewables that fits that description. It doesn't care if the sun is shining or the wind is blowing.
There's another geothermal company in the news this week, Zanskar. They raised $115 million in a Series C round. They seem to be combining the AI and the drilling even more directly.
Zanskar is pure green code meets hot core. They have a slightly different thesis than Fervo. They argue that there's actually plenty of naturally permeable hot rock out there, we just can't see it from the surface. They call it blind geothermal, meaning there are no geysers or steam vents on the surface to tell you where to drill. The resource is hidden. So Zanskar feeds massive amounts of disparate data into an AI model. We're talking gravity data from satellites, magnetic anomaly surveys, seismic reflection data, historical well logs, everything. The AI is trained to find the subtle correlations and patterns in that data that a human geologist would miss.
And what's the success rate on that?
The industry average for wildcat geothermal drilling, just picking a spot and hoping for the best, is about a 20% success rate. Zanskar claims their AI-guided targeting has a success rate of over 80%.
80%, that completely changes the game. That turns exploration from a high-risk gamble into something that looks more like a manufacturing process.
It completely de-risks the upfront capital. If you're a project financier and you know you're going to hit a usable heat resource 4 out of 5 times instead of 1 out of 5, the cost of capital plummets. Financing becomes cheap and easy to get.
One last small tech detail on this caught my eye in the German research reports. A company called Green Therma and their dual vac pipe.
Yes, this is a great example of the practical nuts and bolts engineering that has to happen to make all this work. It's basically a vacuum-insulated pipe designed for a wellbore.
So like a thermos flask, but 3 kilometers long.
Exactly like a thermos. Think about it. You spend all this money to drill 3 kilometers down to get access to 200 degrees Celsius water. But then you have to pump that hot water all the way back up to the surface through 3 kilometers of cooler rock. By the time it gets to the top, it might have cooled down significantly. You lose a huge amount of the energy you were trying to harvest.
So you did all that work for lukewarm water.
Right. Green Therma has built a pipe within a pipe system with a vacuum layer in between that can withstand the crushing pressures at that depth. It insulates the wellbore. It means you get that high-grade, high-temperature heat to the surface, which is crucial if you want to use it efficiently for electricity generation or for district heating.
It's the little things, isn't it? Vacuum pipes and AI algorithms all working together.
That's the convergence we're talking about. The whole stack has to work.
Now, we've talked about all these firm 247 power sources, nuclear, geothermal. But let's ask, why the sudden urgency? Why does it feel like capital is fleeing traditional renewables? The research team flagged a structural break in the 2026 outlooks from several grid operators.
It comes down to the grid reality that parts of the world faced this very week. We had a classic Dunkelflaut.
I love that word. It's German for dark doldrums, right?
It is. It sounds poetic, but for a grid operator, it's an absolute nightmare. For a stretch in late January, specifically across northern Europe and parts of the Midwestern U.S., a high-pressure weather system settled in. That meant wind speeds dropped to near zero, and a thick layer of cloud cover blocked the sun for days on end.
So the wind turbines were just expensive statues.
Giant, motionless lawn ornaments, and the solar panels were producing just a tiny fraction of their rated capacity. The grid operators had to ramp up their natural gas plants to maximum output just to keep the lights on and prevent blackouts.
And this kind of event freaks out the AI companies.
It freaks out everyone who relies on uninterruptible power. It highlights the fact that as we add more and more variable generation, like wind and solar, to the grid, the entire system becomes more fragile and more vulnerable during these weather events. The capital shift we're seeing, money moving out of renewable manufacturing and into firm power assets, is a direct reaction to this reality. Investors now realize that if you want to power the AI revolution, you simply cannot be dependent on the weather. You need the hot core.
But we can't just abandon wind and solar. They are, when they're running, the cheapest electrons we've ever been able to produce. So we need storage.
We do. And not just the 4-hour lithium-ion batteries we've been deploying. We need long-duration storage that can last for days or weeks.
I saw a UK company in the files, Reenergize, doing something interesting with hills.
Right, high-density hydro. Usually pumped hydro storage needs a mountain and a valley. You pump water up the mountain when power is cheap, and then you let it flow back down through a turbine when power is expensive. Reenergize invented a proprietary fluid they call R19. It's a non-toxic, mineral-rich slurry that is 2.5 times denser than water.
So it's just really heavy liquid.
Exactly. And because it's so much heavier, it packs 2.5 times the potential energy for the same change in elevation. This means you don't need a mountain anymore. You can build a pumped hydro system on a small hill. You can even bury the storage tanks underground to reduce the visual impact.
It opens up thousands of potential sites that could never have supported traditional pumped hydro.
It essentially allows for distributed mechanical grid storage. It's clever, low-tech physics being used to solve a very high-tech grid problem.
Finally, there is a note from a Wood Mackenzie report about grid-forming inverters. This sounds very technical, but the research team marked it as crucial.
It is absolutely crucial. This is the software upgrade for the grid. Traditionally, the inverters on solar farms and battery plants are grid following. They look for the frequency of the grid, the steady 60 Hz heartbeat, which is set by the physical inertia of massive spinning turbines at gas, coal, or nuclear plants. The inverters then just match that frequency.
So they're the choir and the big spinning turbines are the conductor.
That's a great way to think about it. But what happens when you shut down all the coal and gas plants?
Who is the conductor? Who sets the beat for the grid?
The grid crashes. There's no inertia, no heartbeat. Grid-forming inverters are a new type of smart inverter that allows batteries to create their own frequency. They provide virtual inertia. They can become the conductor. Wood Mackenzie's report predicts that 2026 is the year this technology goes from niche to standard. It's a critical software upgrade for the grid that allows it to operate reliably with a very high percentage of renewables.
It honestly feels like we are trying to upgrade the operating system of the entire planet while the computer is still running.
That is the best description I've heard all week. And it's a terrifyingly difficult and delicate operation.
So let's try to wrap all this up. Green code, hot core. We've covered the AI-driven scientific discovery, the fusion breakthroughs, the reindustrialization of fission, and the rise of geothermal. What is the big picture here? What's the main takeaway?
The big picture is that we are decisively moving from the pilot project era of the energy transition to the industrialization era.
Yeah.
Look at the numbers we've been discussing all through this conversation. 6.6 gigawatts of nuclear from Meta, a 6 gigawatt SMR program from TVA, a $2.8 billion IPO for a geothermal company. These aren't research grants anymore. This is heavy industry moving at scale.
And the so what for the listener? Why does this matter to them?
The so what is that the narrative of the energy transition is changing. It isn't just about covering deserts with solar panels anymore. It's about a return to physics and density. We are finally tackling the energy density problem head-on. The research notes that nuclear uses 18 to 27 times less land per unit of energy than solar. Geothermal's footprint is even smaller. We are moving toward a future of high-density, high-tech, AI-optimized power.
It's a maturation of the technology and the strategy.
It is. And the most important takeaway is that energy and compute are no longer separate industries. They are merging into a single integrated industrial complex. They are completely dependent on each other.
I want to leave everyone with one last thought to chew on this week. We often talk about our 2050 climate targets, net zero by 2050. That timeline is based on models that assume a certain pace of innovation, a human speed of innovation. But we just spent an hour talking about AI accelerating the discovery process from years down to weeks. So if the green code is real, if it actually works as advertised, if we can really simulate 100 years of material science in a single day, are our timelines wrong? Are our 2050 climate targets, which seems so daunting, actually too conservative? Could we see commercial fusion in the 2030s? Could the green code solve the climate crisis much, much faster than any of our current models predict?
It's the ultimate wildcard. If the AI acceleration is real, then the future arrives ahead of schedule.
I hope you're right. We will certainly be watching. Thank you for joining us on this deep dive for Tomorrow Unveiled. If you enjoyed it, please remember to subscribe and leave a review. It really helps.
Thanks for listening.
This has been Tomorrow Unveiled. Keep looking forward.